All right, good day everyone. So you're welcome to the remaining part of the quantum mechanical harmonic oscillator. That is the treatment of the harmonic oscillator within quantum mechanics. We started this topic before we went for the break, and I'll give a quick recap. So we said for the harmonic oscillator that the Hamiltonian H is given by the sum of the kinetic energy, which is P squared over 2m, plus the potential energy. And we said the potential energy for the harmonic oscillator can be written as half kx squared or half m omega squared x squared. So m is the mass, and omega is the angular frequency. Okay, then we wrote down the Schrödinger wave equation, the time independent one-dimensional Schrödinger equation. We wrote it as, that's for the harmonic oscillator. So we wrote it as minus h bar squared over 2m d squared psi dx squared plus half m omega squared x squared psi equals e psi. So we wrote this equation, and we said that we transformed this equation to a form that does not depend on dimension. That's dimensionless form. So where we transformed it as we transform x to u and so on. At the end of the day, we found that the solution of this equation is psi, if you write it in terms of x with subscript n, which is the different states, because the wave function will have different states. So it's the normalization constant and the Hermite polynomial. So that Hermite polynomial, in our last class, we talked about the properties of the Hermite polynomial. So we said this was the wave function, because when you solve the Schrödinger wave equation, you are solving for the wave functions and the energy eigenvalues. So under the energy eigenvalues for the quantum harmonic oscillator is h bar omega into bracket n plus half. Okay, and we said that this n starts from 0, 1, 2, and so on. So that when n equals 0, that is the ground state. So the ground state, okay, is obtained when the quantum number n equals 0. So in that case, we have psi of 0 and e of 0. So e of 0 will be, we set n to 0, so we have h bar omega over 2. Then we have psi 0 of x. Alright, so in the last class as well, we also began the treatment of the harmonic oscillator using operator method, and we wrote down the two operators, that's the raising operator and the lowering operator. So this is all recap. So let me say recall. Okay, so these are the things that we have done in class. So we said we defined two operators. We defined one as a equals square root of m omega over 2 h bar into bracket x plus ip over m omega. Of course, all these are operators. So this should be hat, this should be hat, and this should be hat. Then the same thing with a dagger. We define that as square root of m omega over 2 h bar, then into bracket x minus ip over m omega. So we have defined this in our previous classes, and also in the last class we showed that. So we have shown that the commutator of a and a dagger equals 1. Then also we have shown that we can write the harmonic oscillator Hamiltonian. Where is it again? So this Hamiltonian star. So we showed in our last class that we can write it as, that's in terms of the two operators a and a dagger, as h bar omega into brackets a dagger a plus half. Okay, we show this, that we can write this, and I think I give you as assignment that so the assignment so I give assignment that you should show that we can also write it in the form h bar omega then a dagger minus half. So you can write it in this form as well. Then the commutator of the Hamiltonian operator against the lowering operator can be written as minus h bar omega a. So you should take note of this. So you should prove this, that we can write the commutator. I think I taught you commutator bracket in our last class as well. So we can write the commutator of the Hamiltonian operator, that is in this form, against the lowering operator a. So the solution would be minus h bar omega a. The same way, the commutator of the Hamiltonian operator against a dagger is h bar omega a dagger. So please show these three relations. This should be 1, 2, and 3. So please show that these three relations are valid. All right, so today, so today we'll start with the number states of the harmonic oscillator. Okay, so number states of the harmonic oscillator. Okay, now we can write the eigenstate of the eigenvalue equation for the harmonic oscillator as the Hamiltonian operator acting on the energy eigenstate n equals En n. You know, recall that we can write the Schrödinger equation as h psi equals E psi. So h is the Hamiltonian, psi is the wave function, E is the energy eigenvalue, psi is the wave function. The same thing, we can write it this way. So this n will be the eigenvectors. Okay, the En will be the eigenvalues, then the h will be the Hamiltonian operator. Then let me see if I've written the I think I've written the energy, so you should note this equation as well, that En is h bar omega n plus half. All right, so we can write h, the Hamiltonian, that is this equation, as En. Recall that our En is h bar omega n plus half. So En is h bar omega n plus half. Okay, then n. So that is because this En is this expression. Okay, let me call this equation 1 for today. Then we wrote here that we can write the Hamiltonian operator as well as h bar omega a dagger a plus half. So we can now write this as, that is this Hn, we can write it as h bar omega a dagger a plus half, I think. Okay, now acting on the state n. Okay, so we can split this bracket to have h bar omega a dagger a, sorry, let me remove the dots, h bar omega a dagger a, then plus h bar omega, sorry, so we have to put the states n plus h bar omega 1/2, then the state n. Okay, now this is for the Hamiltonian operator alone. This one, what we have written here is the energy. Okay, then this h here is, we are using the Hamiltonian operator that we wrote in terms of the raising and lowering operator. All right, so we now have, so Hn equals H bar omega. So let me just label this equation 2. So let's now equate, so let me erase this. So let's equate equations 1 and 2. Okay, so equating 1 and 2. So because 1 we had H acting, the Hamiltonian acting on the eigenvector or eigenstate n is H bar omega n plus half, then the state n. Then in equation 2 we have H bar omega a dagger a n. So we can equate the two equations. So for the case of the second equation, we had H bar omega a dagger a n plus H bar omega over 2 n. So now equals to, so again in equation 1 we split, we expand the bracket so that we have H bar omega n, then the state n, plus H bar omega over 2 the state n. So this and this will cancel out. Okay, so that will be left with H bar omega a dagger a n equals H bar omega n n. So then we can divide through by H bar omega so that we have a dagger a n equals n n. Okay, so let me call this equation 3. Equation 3. So what does this equation 3 tell us? So it tells us that the energy eigenstate of a dagger a is what? Is n. Okay, so this a dagger a is what we refer to as the number operator. So a dagger a is referred to as the number operator. So the number operator is n, okay, and it is a dagger a. So let me call this equation 4. So what does that mean? That means we can write equation 3 as n, because this a dagger a is the number operator acting on the eigenvector or eigenstate n equals small n acting on the eigenstate n. So we can write equation 5 in this form. Alright, so actually a and a dagger, so a dagger is called the raising operator. The raising operator. Why? Because if you want to increase the states of a system, you use the raising operator a dagger. Okay, so technically if a dagger acts on a state, an eigenstate n, so it gives the eigenvalue square root of n plus 1, and it increases the eigenstate by 1. Okay, so when a dagger acts on the state, it increases by 1 with this normalization factor. Then let me call this equation 6. When a, which is a lowering operator, so a is called the lowering operator. Okay, so when it acts on a state, it reduces the state by a step. Okay, so when it acts on a state, you have a constant, then the state will now reduce by 1. Okay, so this is the reason why this a is called the lowering operator, because it lowers the state, and this is called the raising operator because it increases the states by 1. Okay, so in general, if you want to raise maybe okay, let's do this. If you need a state, if a dagger acts on state 0, okay, a dagger, so what we are using equation 6 now. If it acts on state 0, it means n is 0. So this will be square root of 0 plus 1, Abi, then 0 plus 1. Then this will be 0 plus 1 is 1, square root of 1 is also 1. 1, then 0 plus 1, 1, or the states 1. Okay, so that means that if a dagger acts on state 0, it gives what? State 1. Then if A dagger acts on state 1, so it will be when A dagger acts on state 1, then it will be the normalization constant, which is square root of n plus 1, so it will be square root of 1 plus 1. Okay, then state n plus 1, so which is 1 plus 1, that is 2. So it means in that case it will be square root of 2, then 2, and so on and so forth. Okay, so in general, if you want to produce n states, maybe 10 states, then what you do is you do 1 over square root of n factorial, then A dagger raised to power n, then the state 0. So you want to create states maybe 5, then it means you apply this operator 5 times on the state 0. Okay, so that is about that. Now you should know that also that when the number operator, the commutator of the number operator on the lowering operator, it gives negative minus 1 multiplied by the lowering operator. How do we prove this? We prove this by using the definition of the number operator, which is A dagger A. Okay, recall that the number operator is A dagger A, this equation, A dagger A. Okay, so you close the bracket, so comma, then A. So now this, recall from our commutator, you know, when you have the commutator bracket of A comma B, the answer is AB minus BA. Okay, if you have A, maybe A, B comma C, okay, the commutator will be A outside, then B comma C, then plus A comma C, then B. Okay, so we now apply this, we apply it here, that this one will be A, B, C. So the commutator of A dagger A against A will be, we'll first put A dagger outside, then we have, it should be commutator bracket, then A comma A, then plus, so you put A dagger in here, comma A, then you put A outside. So just use this formula. Okay, now we learned in our last, so let me see if it's part of the so this equation, so let me call it the equation star. So that A dagger, commutator of A dagger equals 1. We learned that in our last class as well. So commutator, so of recall, so let me say recall that the commutator of A dagger equals 1. It means that the commutator of A dagger A will be what? Minus 1. But when they are the same, A and A are the same, then this will be 0. Okay, so this will be 0. Then it means we have the commutator bracket of A dagger A comma A will be A dagger multiplied by 0, then plus, now A dagger is minus 1, so that will be minus 1, then multiplied by A. So this will now be minus 1 times A, because A times 0 is 0. So therefore the commutator of the number operator and A is what? Minus A. So what about the commutator of the number operator and A dagger? Okay, what will it give us? So again, you use the same principle. So the number operator is A dagger A, so A dagger A comma A dagger. So we use the same principle, so that this will be A dagger A comma A dagger, then plus A dagger, then A. So that again, this A dagger will be 0, because the commutator of an operator with itself is 0. Then so that this one will be A dagger. Now the commutator of A and A dagger is 1, so plus 0, so that will be A dagger. So in summary, the commutator of the number operator with A is minus 1, and the commutator of the number operator with A dagger sorry, it's minus A, minus A, minus A. Then this one is A dagger. Okay, and so that is where we stop for today. Okay, so see you next week.